The Rockwell International video explores the complex world of stealth technology, detailing advancements in aircraft design and capabilities initially created for military applications, but later adapted to civilian and commercial sectors. Key concepts explained include radar cross-section, radar absorbent materials, airframe shaping, engine inlet and exhaust treatments, and integrated control. Radar cross-section is a measure of how detectable an object is by radar. A larger radar cross-section indicates that an object is more easily detected by radar, while a smaller radar cross-section indicates that an object is less detectable. The video explains how the radar cross-section of an aircraft is reduced to minimize its detectability by radar systems. This is achieved through various methods, including shaping the aircraft's surfaces to deflect radar waves, using radar absorbent materials to absorb radar energy, and minimizing the number of radar reflective components in the aircraft. Radar absorbent material is a type of material that is designed to absorb radar energy. When radar waves strike a radar absorbent material, the energy is converted into heat, which is then dissipated into the material. This reduces the amount of radar energy that is reflected back to the radar source, making the object more difficult to detect. The video introduces the use of specialized materials that absorb radar energy, further decreasing the radar cross-section. These materials are often applied as coatings to the aircraft's surfaces, or they may be incorporated into the aircraft structure. Airframe shaping involves designing the aircraft's shape and contours to minimize radar reflections. This is achieved by using smooth, curved surfaces that deflect radar waves away from the radar source. The video demonstrates how the aircraft shape and contours are designed to limit radar reflections. Sharp angles and flat surfaces are avoided, as these tend to reflect radar waves back to the source. Engine inlets and exhausts can be significant sources of radar reflections and heat signatures. The video shows how engine inlets and exhausts are engineered to reduce the detectability of heat signatures. This may involve using shielding to block radar waves from entering the engine, or using special coatings to reduce the heat signature of the exhaust. Integrated control highlights the importance of coordinating and optimizing all stealth features within a comprehensive system. This means that the various stealth technologies must work together seamlessly to achieve the desired level of stealth. Applications of stealth technology are far-reaching. The video emphasizes the versatility of stealth technology, showcasing its applications in military aircraft, enhancing the survivability of fighter jets, bombers, and reconnaissance planes, commercial aircraft exploring the potential for reducing fuel consumption and improving aerodynamic efficiency, and unmanned aerial vehicles enabling missions with increased autonomy and covertness. In military aircraft, stealth technology is used to reduce the detectability of aircraft by enemy radar systems. This allows military aircraft to operate in contested airspace with a reduced risk of being detected and attacked. Stealth technology can also be used to improve the survivability of military aircraft by making them more difficult to target. In commercial aircraft, stealth technology can be used to reduce fuel consumption and improve aerodynamic efficiency. This is achieved by reducing the drag on the aircraft, which allows it to fly faster and further on the same amount of fuel. Stealth technology can also be used to reduce the noise pollution generated by aircraft. In unmanned aerial vehicles, stealth technology enables missions with increased autonomy and covertness. This is because stealth technology makes it more difficult to detect and track these vehicles. This allows unmanned aerial vehicles to be used for a wider range of missions, including surveillance, reconnaissance, and attack. In conclusion, the Rockwell International video concludes by emphasizing the ongoing advancements in stealth technology and its potential impact on diverse industries. It leaves viewers with an appreciation for the ingenuity and complexity involved in developing and utilizing this cutting-edge technology. The development and implementation of stealth technology involves a multifaceted approach, encompassing not only materials science and engineering but also advanced aerodynamics, propulsion systems, and electronic warfare techniques. The integration of these disciplines is crucial for achieving a truly effective stealth capability. The challenge lies not only in reducing an aircraft's radar cross-section, but also in minimizing its infrared, acoustic, and visual signatures. Modern radar systems are becoming increasingly sophisticated, employing techniques such as frequency agility, pulse compression, and moving target indication to enhance their ability to detect stealth aircraft. As a result, the development of stealth technology is an ongoing arms race, with each side constantly seeking to outwit the other. The use of radar absorbent materials, or RAM, is one of the most common methods of reducing an aircraft's radar cross-section. These materials are designed to absorb radar energy, converting it into heat or other forms of energy that are dissipated into the material. There are several different types of RAM, each with its own advantages and disadvantages. One type of RAM is made from a composite material consisting of a matrix of polymers or ceramics embedded with conductive particles. These particles absorb radar energy through a process called dielectric loss. Another type of RAM is made from a thin film of metal or other conductive material that is applied to the surface of the aircraft. This film absorbs radar energy through a process called resistive loss. The shape of an aircraft can also have a significant impact on its radar cross-section. By carefully shaping the aircraft's surfaces, it is possible to deflect radar waves away from the radar source, making the aircraft more difficult to detect. This is often achieved by using smooth, curved surfaces and avoiding sharp angles and flat surfaces. The design of engine inlets and exhausts is another important consideration in stealth aircraft design. Engine inlets and exhausts can be significant sources of radar reflections and heat signatures. To minimize these signatures, engineers often use shielding to block radar waves from entering the engine, and they may also use special coatings to reduce the heat signature of the exhaust. Integrated control refers to the coordination and optimization of all stealth features within a comprehensive system. This means that the various stealth technologies must work together seamlessly to achieve the desired level of stealth. For example, the shape of the aircraft must be carefully designed to complement the use of radar-absorbent materials, and the engine inlets and exhaust must be designed to minimize both radar reflections and heat signatures. Stealth technology has a wide range of applications, both in the military and commercial sectors. In the military, stealth technology is used to reduce the detectability of aircraft, ships, and other vehicles. This allows military forces to operate in contested airspace or waters with a reduced risk of being detected and attacked. Stealth technology can also be used to improve the survivability of military vehicles by making them more difficult to target. In the commercial sector, stealth technology is used to reduce fuel consumption and improve aerodynamic efficiency. This is achieved by reducing the drag on aircraft and other vehicles. Stealth technology can also be used to reduce the noise pollution generated by aircraft. The development of stealth technology has had a significant impact on the design of military and commercial aircraft. Stealth aircraft are typically more expensive and complex to design and manufacture than conventional aircraft, but they offer significant advantages in terms of survivability and mission effectiveness. The future of stealth technology is likely to involve the development of new materials and techniques that further reduce the detectability of aircraft and other vehicles. One promising area of research is the development of metamaterials, which are artificial materials that have properties not found in nature. Metamaterials can be used to create cloaking devices that can make objects invisible to radar and other forms of electromagnetic radiation. Another area of research is the development of adaptive stealth technologies, which can change the stealth characteristics of an aircraft or vehicle in response to changing environmental conditions. Stealth technology also extends beyond the realm of aviation, finding applications in naval vessels, land vehicles, and even individual soldier equipment. The principles remain consistent, minimizing signatures across various detection methods, but the implementation varies depending on the specific platform and operational environment. Stealthy naval vessels, for instance, incorporate hull designs that deflect radar waves, along with radar-absorbent coatings and measures to reduce acoustic signatures. Land vehicles employ similar radar-absorbent materials and shaping techniques, while also focusing on minimizing thermal and visual signatures. Individual soldiers can benefit from stealth technologies through the use of camouflage, specialized clothing that reduces infrared signatures, and communication systems that minimize electromagnetic emissions. The integration of stealth technologies into these diverse platforms requires careful consideration of factors such as cost, weight, performance, and maintainability. There is often a trade-off between stealth capabilities and other performance characteristics such as speed, payload, and range. Ultimately, the optimal stealth solution depends on the specific mission requirements and the operational environment. The ongoing evolution of stealth technology is driven by the continuous advancement of detection technologies. As radar systems become more sophisticated and capable of detecting smaller and fainter signals, stealth technologies must adapt to maintain their effectiveness. This constant cycle of innovation ensures that stealth technology will remain a critical area of research and development for years to come. The development of stealth technology has also raised ethical considerations. Some critics argue that stealth technology can make it easier for military forces to conduct covert operations, which could lead to increased civilian casualties and other unintended consequences. There is also concern that the proliferation of stealth technology could destabilize international relations by making it more difficult to deter aggression. These ethical considerations highlight the importance of careful oversight and regulation of stealth technology to ensure that it is used responsibly. In addition to the technical and ethical challenges associated with stealth technology, there are also significant economic challenges. The development and deployment of stealth technology can be very expensive, and the cost of maintaining stealth capabilities can also be substantial. As a result, only a few countries and organizations have the resources to develop and deploy advanced stealth technologies. This can create a strategic imbalance, as those with stealth capabilities may have a significant advantage over those without. The future of stealth technology is likely to be shaped by a number of factors, including technological advancements, economic constraints, and ethical considerations. As new technologies emerge and detection systems become more sophisticated, stealth technologies will need to adapt to maintain their effectiveness. The economic costs of stealth technology will also continue to be a factor, as countries and organizations must weigh the benefits of stealth capabilities against the costs of developing and maintaining them. Finally, ethical considerations will continue to play a role in shaping the development and deployment of stealth technology, as policymakers grapple with the potential implications of this powerful technology. Ultimately, the future of stealth technology will depend on how these factors are balanced and managed. The video provides a valuable overview of the key concepts and applications of stealth technology, highlighting the ingenuity and complexity involved in developing and utilizing this cutting-edge technology. It also raises important questions about the ethical and economic implications of stealth technology, prompting viewers to consider the broader societal impact of this powerful technology. The principles of stealth technology can also be applied to other areas, such as cybersecurity. By understanding how to minimize the detectability of computer systems and networks, it is possible to improve their security and resilience against cyber attacks. This involves techniques such as encryption, steganography, and network traffic obfuscation. Encryption is the process of converting data into a form that is unreadable to unauthorized users. This helps to protect sensitive information from being intercepted and accessed by attackers. Steganography is the practice of hiding information within other, seemingly innocuous data. This can be used to conceal the presence of malicious code or to communicate secretly without arousing suspicion. Network traffic obfuscation involves disguising the characteristics of network traffic to make it more difficult for attackers to identify and analyze. This can be achieved through techniques such as traffic shaping, protocol spoofing, and port hopping. By applying these techniques, it is possible to create computer systems and networks that are more difficult to detect and attack. This is becoming increasingly important in today's world as cyber attacks are becoming more sophisticated and frequent. In addition to the technical aspects of stealth technology, there are also important organizational and procedural aspects. For example, it is important to have clear policies and procedures for managing access to sensitive information and systems. It is also important to train employees on how to identify and avoid phishing attacks and other social engineering tactics. By implementing these measures, it is possible to create a culture of security that helps to protect against cyber attacks. The video effectively demonstrates the core pillars that are behind the technology. Firstly, it minimizes radar reflections. Secondly, it absorbs rare energy. Thirdly, it manages heat signatures. Fourthly, it utilizes integrated control systems. Stealth technology is a multifaceted field that requires expertise in a variety of disciplines, including materials science, aerodynamics, propulsion, and electronics. The ongoing advancements in these fields are driving the development of new and improved stealth technologies. As detection systems become more sophisticated, stealth technologies must continue to evolve in order to maintain their effectiveness. This constant cycle of innovation ensures that stealth technology will remain a critical area of research and development for years to come. The video serves as an excellent introduction to the complex and fascinating world of stealth technology. It highlights the key concepts, applications, and challenges associated with this technology, and it prompts viewers to consider the broader societal implications. The information can be used by professionals and students alike.